In the early years of numerically controlled machining, production speeds accelerated rapidly. However, verifying the accuracy of those parts remained a manual process, requiring inspectors to physically handle and position every component for checking. Relying on a human to interpret a surface plate or a vernier caliper introduced the variable of operator feel. This subjective physical interaction with analog tools was slow and frequently resulted in measuring errors that could compromise an entire production run. To address this inconsistency, engineers developed the Coordinate Measuring Machine, or CMM. The CMM works by mapping a physical object's geometry into a 3D Cartesian coordinate system. This is a mathematical framework that uses x, y, and z axes to define any specific point in space. By probing the part, the machine records these coordinates with precision as high as 2.5 micrometers. This shift means the CMM functions as a specialized industrial robot. It is designed to capture the specific geometric properties of a part through automated, repeatable movement rather than human estimation. Moving a sensor through 3 dimensions with micrometer accuracy requires a rigid frame. The bridge type is the most common configuration, utilizing a traveling structure that moves across the measuring table to carry the sensor. For different workflows, the cantilever design uses an open-sided construction. This allows large parts to be placed on the table without the machine's frame obstructing entry. When components reach the scale of full car bodies or massive dies, manufacturers employ Gantry CMMs. These large-scale systems use overhead supports to move the probe across an expansive horizontal plane. While these main structures provide the movement, the actual data is gathered by the probe system, the machine's primary interface with the part. Probing technology has evolved from simple solid plugs to motorized heads capable of 720 distinct orientations. This articulation allows the machine to reach into deep holes and complex recesses that would be unreachable with fixed tools. Regardless of the machine's configuration, every structural element is designed for one task, positioning a sensor to accurately record a touch point on a physical surface. Accuracy requires 5 steps. 1. Homing defines the global machine coordinate system. 2. Qualifying the tip calculates a mathematical offset for the probe's diameter. 3. Aligning the part establishes a local coordinate system directly on the angled workpiece. Step 4 is the measurement phase. The probe makes contact with the part, either physically or through optical sensors, triggering a signal that records its exact position in space. As the probe records points, it creates a point cloud. This dense collection of discrete coordinate data represents the physical surface area of the component. Step 5 is representation. Software analyzes the point cloud to calculate dimensions and form deviations, generating a report to confirm if the part meets specifications. This sequence effectively translates a physical workpiece into a digital dataset, providing a basis for automated geometric inspection. Modern CMMs use regression algorithms to construct geometric features from the point cloud. This mathematical analysis verifies that the finished part aligns with the tolerances of the original design. When the process is fully automated, it is known as Direct Computer Control, or DCC. With this system, a DCC CMM can be programmed to measure identical parts repeatedly without human intervention. This automation provides significant flexibility. Because the probe makes very light contact, many parts can be inspected without being clamped down, eliminating the need for expensive, custom-made fixtures. It also reduces setup time. Software can automatically define the orientation of a part, so the operator no longer needs to spend time manually aligning the workpiece to the machine's axes. Most importantly, the machine removes subjective operator influence and transcription errors. Digital readouts provide data that is independent of an inspector's individual feel for an instrument. With these programs in place, operators can perform complex inspection procedures with high consistency. The machine handles the micrometer-level precision, while the human role shifts towards overseeing the automated system. Replacing manual interpretation with 3D coordinate data, the CMM provides an objective standard for quality control. This automated workflow allows manufacturers to verify that physical components remain faithful to the original digital models used to design them.
Thanks for watching and grow every day with just a bit of information. Like, share, and subscribe for more content and learning.